We couldn't be in person meeting in Lisbon this year. Okay, maybe for the next edition of ECIR. So we're trying to do the best we can under these settings. And overall, so far, I think it's the conference has been going on quite well. So yeah, so during this first session, we'll actually be having two different talks. Okay, so we had a third one planned, but unfortunately, the third speaker could not be with us today. And throughout the day, we'll actually be having 7 different Industry Day presentations, plus a keynote address at the end of the day. Okay. Same as happened here in this session. So to the other, well, eventual speakers that are now on the call as well, try to be on the Zoom webinar a bit before your session starts. Okay, raise your hands and we'll promote you to attendee, to panelists, so that you can share your screen and turn on the microphone. And after each talk, okay, so if you have questions, please do raise your hands as well. Or if you prefer, leave the questions on the Q&A. We'll try to take a look at those and also post them here and ask them here. Okay, so I think we'll have plenty of time for interaction. Okay, during the Industry Day sessions. Okay, so yeah, given this introduction now, so given these announcements, okay, we can move on and start with the first presentation. Okay, so Manish is coming from Microsoft Research India, and yeah, his talk is going to be focused on challenges, let's say, associated to the practical deployment of these very large language models, okay, that nowadays are used for NLP and retrieval applications. Okay, so Manish, you already shared your screen, so when you're ready, I guess you can start.
Absolutely. Thank you so much, Bruno. Also, thanks to ECIR for helping us present this talk at ECIR Industry Day. Right. So the talk, as Bruno also mentioned, is going to be on challenges and lessons learned from these large-scale deployment of transformer models. Transformer models have become sort of mainstream these days, right? Like since 2018, like past 2 years, I think there has been several deployments inside Microsoft which are based on transformer models. But the major problem around these deployments is that these models are pretty large in size. So as you may have known, right, the T5, which Google basically put out a few months back, is about 26 GB in size, right? And Microsoft also has its own internal models, which are much larger actually, right? So how do you take care of those when you are deploying these things? And I'm going to go over a case study. This case study is about question answering. In fact, Bruno, as we were talking just before this, right? So, the idea is as follows. You find lots of chatbots on various websites these days. And these chatbots are actually very useful, both for enterprises and the users who use them, right? So, and specifically in this particular talk, I'm going to talk about FAQ answering problem, which is basically, let's say there's an enterprise and they have a whole bunch of FAQ pages. For example, some bank, and they have a lot of FAQ pages on their website. Now, they want users to read these FAQ pages and make sense out of them. But users find them very lengthy to read, and therefore they would be much more happier if the enterprise creates a chatbot out of those FAQ pages and gives them an interface where they can just type in the query on the chatbot and get their question answered quickly. Right. So the technical problem definition is, given a set of FAQ pages S for an enterprise and a user query, the new thing that the user has just typed in, we want to find the best matching question answer pair from a database S and answer that. So we experiment with multiple transform models in this particular in this work, and majorly our model is MTDNN, which is multitask deep neural network, further based on BERT actually, right? But we also modify it to come up with something called as masked MTDNN or MMTDNN. We propose a knowledge distillation component as well, which is like semi-supervised learning, so as to improve the quality of your model. Which helps us achieve like 2.4x reduction in model size and about 7x reduction in runtime while maintaining similar accuracy numbers. We show our results on 2 data sets. One is a public benchmark, SemiVal 2017, where we get an NDCG at 1 of like 83.1. And the other is our own data set, which has been created using Bing. So it has like 281K instances. and our distilled model, which is like just 174 MB, provides an NDCG at 1 of 75.8 and a CPU runtime, mind you, not a GPU runtime, but a CPU runtime of just 31 milliseconds. Right? So, and that's basically pretty good. So it's very, so I don't need to really motivate why chatbots are important, but very quickly, chatbots are important both for enterprises who do not want to who want to deflect as many calls away from the call center as possible to reduce agent costs, and also to give a very good experience to customers. Because well, to avoid call center calls, they have FAQ pages, but FAQ pages are long. Answers may be spread across multiple pages or across multiple questions in the same page. So overall, it's a pain, even when pain for the users, even when enterprises have FAQ pages. So they would very much want some software which basically takes their FAQ pages and automatically creates chatbots out of them. Right? And users also want chatbots because they do not want to keep calling call centers and wait for folks to answer their calls, or email them, or post their questions on community question answering forums, get the answers, and so on. So with that view, the idea is given a database of question answer pairs and a new query that the user has just typed in, we want to get the best matching question answer pairs. Now, I'm saying pairs rather than just a pair, because when you see the right chatbot interface, the one on the right side, well, there you only want to have one question answer pair, and you want to show the answer from the best matching question answer pair. Right? However, you might also have another kind of search kind of interface, which you see on the left side, where the user may type in a query like, I am traveling, how can I get OTP, right? One-time password. So, and this is like a US bank customer. So they want to know all possible matching pairs. So now here we want to show like 4 pairs. So therefore the idea is, well, we want to rank question answer pairs, and some applications may just want 1 pair, like on the right side, while some may want more pairs, like on the left side. So this work, there is quite some related work. Interestingly, FAQ web pages have been studied previously a lot. In fact, very old pieces of work which tried to figure out FAQs from list, using list detection algorithms. So we also use some of those algorithms to actually gather FAQ FAQ question answer pairs from FAQ pages. There's also work on answering questions using FAQ web pages, very related to the work that we have been doing. But using traditional feature engineering kind of methods, or using some sort of deep learning methods, but not quite transformer models, which give us reasonably very good accuracy. So there's also work on building navigational interface for FAQ pages, or completeness of FAQ pages, which is actually our own work in Wisdom this year. In fact, we had this work where we tried to figure out whether FAQ page is complete or not, or can the enterprise add more questions to it, right? So and then all of us know that transformer models, there are several applications since transformer, Vaswani et al. Put up the transform paper, and then BERT, and then Devlin's BERT, and then MTDNN, Robert, and so on. So multiple models have come in, which have found application across NLP tasks like text classification, entailment, machine translation, word sense disambiguation, etc. So lastly, we also care about model compression, because hey, that is the main part. We do want to solve this challenge. How do we actually ship these models? We can create these models. Accuracy is great. Offline, it's awesome. But hey, when you want to ship them, if you don't have GPUs, can you still live without GPUs? Right? So, and as we saw, we will see techniques which can lead to CPU runtime which is bearable. There are many techniques which have been proposed in the literature: pruning, quantization, knowledge distillation, low rank factorization, and so on. So each of them have their pros and cons. We stuck to knowledge distillation. We found knowledge distillation really gives us very good results. So this is the broad idea. Given a question answer database, when a user query queue arrives, we first compute a list of candidate QA pairs which have high BM25 scores. So the first level 1 ranking in that census is to just use BM25 and find those candidates which can potentially be the answers for this query. Now these candidate QA pairs, along with the original query, are then scored using various methods that I'll talk through next. In fact, that is the core of our work. Top QA pairs with high scores are then returned to the user. In the chat interface, it's just the top 1. K is set to 1. Right? So these are the 4 methods we tried. Now, of course, A and B are baselines, and C and D are our methods. So A is a vanilla bile STMs with attention. So essentially, remember, we have we have a candidate QA pair. So you have a question and an answer, and the current user query. So you have three things, and you want to figure out how well they match. So the best way is to really encode them using BILSTMs, and yes, of course, BILSTMs with attention, and maybe start. So we use two rows and put a MLP at the top and get the final output, which basically says whether they match or not, or maybe gives a grading like good match, bad match, fair match, and so on. Right. So B is the SymByMPM baseline. It was in ECIR, I think 2 years back. So in this particular work, they actually have something called as a match block, which is sort of computing like a cross attention across question and query pair, or across answer and query pair. Right. So and then we noticed that, hey, if you want cross attention, why not make use of transformers? They have attention everywhere. I mean, it's basically a huge lot of attention, self attention in the transformer encoders. Right. So that is why we came up with this C thing, which is not our contribution as such, but application of transformers for this problem. So we said that, hey, we will feed the query, question and answer to the transformers as input, the same vanilla 12-layer transformer encoder, of course, prepended with a CLS token and separated by SEP tokens, so that we have three different segments. We trained it over a large corpus, and then we wanted to test it over the small benchmark corpus. Right? So that's C. And then we have D, which is, maybe a little bit more detail about C. So it's like a 12-layer BERT, and it has been fine-tuned, or rather, it has been pre-trained. As we know, BERT is pre-trained on books, corpus, and Wikipedia. So we started off with that one using the unsupervised MLM and NSP losses, mass language model, and next sentence prediction losses. So that was basically the BERT kind of transformer encoder. We also tried MTDNN transformer encoder, which is like an extension of BERT from a multitask perspective, where it tries to pre-train using 4 different kinds of tasks: single sentence classification, text similarity, pairwise text classification, and relevance ranking tasks. So again, the format remains the same. We take CLS token, query, SEP, question, SEP, and then answer, and pass it to this MTDNN transformer encoder, and get the final output. Okay, get the final output from the representation for the CLS token, which is basically the C. And then once we have that representation, we pass it on to the final output softmax layer. Right. So this is our contribution, MMTDNN, masked MTDNN as we call it. So what we do is to really have this transformer encoder split into 3 parts in some senses. So rather, I will call it 2 parts. So the first part essentially is the same. And remember, the original transformer has 12 layers. So we have a transformer encoder 1, which is which we call as like L layers, right? And then 12 minus L layers are sort of split among these 2 transformer encoder 2s. Okay. So now the transformer encoder 2, the first encoder 2 actually gets input as query and question only, while the second encoder 2 actually gets question and gets basically query and the answer. Okay. So the first one gets query and the question, second one gets query and the answer. In some senses, this idea is sort of borrowed from the baseline, from one of the baselines, which also says, hey, query question match should be evaluated separately, query answer match should be evaluated separately. And that does make sense as well, right? If you think of it, somebody asks what is the price of XYZ, maybe the question also is like, what is the cost of XYZ? But maybe the answer would just be like $100, right? And you want to basically match price with cost and price with $100, right? So semantically, it's different things. And therefore, it does make sense to have different kinds of encoders paying different kind of self-attention across query question or query answer. So that's basically that, right? At the end, we basically take the C tokens from both of them and then concat and then finally connect to the output softmax layer. So that's our major approach. Now, coming to the important part, we basically found that, hey, we could tune it using our labeled data, but our labeled data is too small. And therefore, what we did was use knowledge distillation so as to do multiple things. 1, improve the accuracy of our model. 2nd, decrease the size of our model. So we start with a teacher model, which is our MMTDNN 12-layer model, but our student model is just an MTDNN with 3 layers only. Okay. We basically do transfer learning, initializing our initial student model using layers 2, 3, 4. We basically tried other layer combinations also from the teacher model. Okay. And then we do knowledge distillation on it. So knowledge distillation meaning using the same labeled data, but with a soft loss, and then distill this initial model so as to get a distilled student model, and finally use a large amount of unlabeled data so as to and again use a soft loss based on the distribution we obtain, prediction distribution from the teacher model, so as to further tune this model to get the final distilled student model. Now, so as to facilitate gradual knowledge transfer, basically do it in multiple steps. We sort of take it from 12-layer to 9-layer to 6-layer and then to 3-layer. But to make the diagram simple, I've directly shown from 12-layer to a 3-layer model. Again, we also do other kinds of optimizations, which some other teams in Microsoft have made available for us for free. They are also called as TVM compiler optimizations. So the deep learning compiler itself, you can optimize a whole bunch of things out there. There's also published paper actually, right? So as to further get more optimizations. The evaluation we do on 2 data sets. So first one is a benchmark data set. It's pretty small, as you see in the table. It has like a few hundreds of queries and a few thousands of question answer pairs, versus our data set, FAQ search data set, which is our own data set, and we have like tens of thousands of queries, and 0.1 million ordered question answer pairs, right? So a few hundreds of thousands of question answer pairs. So this is the, our data set is actually obtained using Bing queries that lead to FAQ pages, that lead to clicks to FAQ pages. And we got them judged into good, average, or bad pages, a good, average, or bad question answer, by extracting question answer pairs from these FAQ pages. So the judgment was done, at Microsoft, we basically made sure that these question answer pairs are pretty representative. So we have taken FAQ pages across various domains like airports, banks, supermarkets, tourism administrative bodies, all kinds of categories of enterprises. We also made sure that queries and QA pairs are of various sizes and have and FAQ pages with varying number of QA pairs. So some had like 5 pairs, some had like 50 pairs, and so on. So glove embeddings were used for initial embedding for query, question, and answer, which was supplied to the transform models. The transform methods used word piece embeddings. For the bias teams, etc. We used glove embeddings. We used typical GPUs. NDCG at K is the metric that we use. Finally, we also report numbers on CPUs, right? For bias teams, we used a hidden layer 300 size, and for transformers and so on, we used about 30,000 sized vocabulary. So here are the results, and these are the accuracy results. Now what we see here is that for both the different both the data sets, semi-val and FSD data sets, and we have results for the baselines, and we have results for our methods. Again, we could pre-train or just pre-trained model we could use, or we could use fine-tuned ones. Of course, fine-tuned ones give us better accuracy. So, and what we observe is that MMTDNN actually performs the best among all of those methods, the ones that we proposed. Also, in semi-val, in fact, besides the query, they've also provided a query subject and a query body in some senses. So it's more like a Quora kind of setting where you have a query subject and a body. So if we use both of them, which is shown on the right side of this slash, right, we basically see that the results are somewhat better than just using the query. So more context essentially helps. Right? Again, this chart basically shows the NDCG at K values for our approach. So, and it's sort of intuitive in the left chart that, hey, as you increase the position, your NDCG at K improves, which is great for FSD dataset. But for semi-val dataset, somehow that doesn't happen. And we are wondering why, right? And then we realize that, hey, semi-val is a very small dataset, so it does not really have too many matching questions for a particular query. So, as you increase K, the nearest neighbor that you get basically gets too far away, and therefore the NDCG does not really seem to be improving for the small dataset. Also on the right side, we show what happens when you vary the size of the encoder 1. And you see that, in general, the size of encoder 1, essentially the accuracy or the NDCG sort of seems to improve if you have L larger. So essentially, it means that, hey, it is good to actually have a lot of self-attention across query, question, and answer in the initial few layers. And then at the last 1 or 2 layers, basically let it have individual attention for query, question, and query, answer. So I know I'm not, we don't have a lot of time, so I'll skip this example. But there are these queries and question answer pairs that we derived, which looked very, very reasonable. For example, if I have, the queries, I have paid for my parking, but my flight is delayed, right? And then we showed things like what happens if I exit the car park prior to my confirmed time, or later, or enter the car park later and amend or cancel my car park booking, and so on. We also did attention visualization of the last layer for our MMTDNN model, and we saw that so these are basically attention. This is the query. So the first, second, and third, there are 3 things: query, question, and then you have in the middle query answer attention, and in the right side you have question answer attention. So basically, query, if the query was about delayed, well, it has a lot of attention on prior, time, later, time, and so on in the question, which is very intuitive, and so on. So we found this as a very, very intuitive and explanations. We also did some error analysis and found that, hey, model makes errors mainly because of some sort of entity mismatch or intent mismatch, and so on. Now, the most important slide is this with regards to knowledge distillation, right? So we tried to, so our MMTDNN best model, great accuracy, 417 MB, and Microsoft said, well, we can't ship this model. very difficult because, hey, that requires a CPU runtime of 225 milliseconds, right? Now we had to bring this down so as to convince our folks, executives, to be able to help us ship this. And that is where actually half of the journey started. And that is where, so we basically did knowledge distillation, as we discussed, using unlabeled data and so on. Our accuracy remained almost the same. But what happened is that CPU runtime reduced drastically to like 31.4. And our model size reduced to like 174 MB. And that was like a super wow. So, I mean, pretty happy with the model. This model is shipped now, and and doing good. So what you see on in this chart is basically size. So we have on the x-axis latency, so prediction time prediction time latency. On the y-axis you have accuracy, so NDC at 1, and the bubble size actually indicates the size of the model. So these two are baselines, very small latency, but accuracy is poor anyway. And these are other methods, like all transformer-based methods. And we are bubble 8, essentially, low latency and high accuracy, and the model size is reasonable. It's not too bad. So in conclusion, we propose the use of transformer models like BERT, MTDNN for solving the FAQ answering task. So that is also a contribution. Of course, it's not new, but a new application for sure. But we also proposed a new architecture of MTDNN, which basically gave us better results compared to just MTDNN or just BERT, right? Even when fine-tuned. Further, we proposed experimented with the knowledge distillation strategy, which actually was the thing which allowed us to ship this model. Overall, the proposed techniques lead to models with high accuracy, small runtime, and small model size. So I think I'll stop here and take questions. So yeah.
Okay, thank you, Manish. So unfortunately, you won't be hearing a huge crowd, clapping. You'll probably just hear me.
Oh, thank you so much. Thank you. Yeah, happy about that. But any questions? Would love to take. Yep.
Yeah, so we can take questions either on the Q&A or if you raise your hands, or just, well, leave them on the chat as well.
Absolutely.
I'll maybe start with one, as people type in. And which relates to, well, the different models that you presented and the fact that these transformer-based models, in your case, they were, let's say, modeling together the queries, the questions, and the answers, right? So,
yes,
they always start by concatenating these textual representations, right? And building then a representation from that.
Correct.
So,
exactly.
So have you tried models in which the different parts are represented separately with transformers and afterwards modeling the interactions? Because through something like that, you would probably benefit on efficiency, right? On the sense that, for instance, you could pre-store the representation.
So yeah. I mean, Pablo, you're giving away, Bruno, I think that's Bruno speaking, right? So you're giving away the idea. I mean, exactly. So, so as to make it feasible, that is the other trick that we did. And possibly we'll put it out as a separate paper at some point. So, what we did, exactly as you said, you have the question answer database. Every time a query comes in, you don't want to do all those computations. So yes, we have the query question encoded separately. Accuracy, honestly, so accuracy does not improve, but of course, it basically saves on time significantly, because all you need to do is to now encode the query. Yeah.
Okay, but in that scenario, does the accuracy drop significally, or no?
It doesn't drop significantly. Actually, we have an adapter layer at the top, so we do have some sort of interactions being captured at the top. We do not have 12-layer deep kind of interactions, but we do have something at the top. So in fact, if you look at our MMTDNN model, so we did try essentially separately encoding query question and query answer, right? So when L is set to 0, effectively that is what we tried. So, but that doesn't really give us the best accuracy. I mean, it does give reasonable accuracy, but that doesn't also give us any performance gains, right? Because hey, you would be processing query question and query answer both at the runtime. But of course, processing query question answer at the separately and query separately gives us that real good benefit of saving on query on question and answer transformations at runtime.
Okay.
So that's great. In fact, there are some things on the chat also. So yeah, we did refer to FAQ Finder, Joshen. So yeah, I mean that was the original paper on mining question answer pairs. how do you serialize the model and measure the quoted latency? Is it protobuf loaded with Java? So we did experiments on PyTorch, and we basically so essentially we did basically everything using PyTorch. So and Georgios, basically it's basically all loaded in the RAM at runtime. So essentially, when we talk about latency, it's basically from the loaded model in RAM. Any particular preprocessing for numerical values and locations, or the model takes care? It all takes care. No, we did not really do any particular preprocessing, Georgios. So no particular preprocessing. Yep. Thank you. As an open source for models B and D? No, unfortunately. In fact, we actually emailed the authors of B. So now it turns out they are at a company called Intuit. And unfortunately, they were not able to share the code for B at all. For D, we will look at, I think model code surely can be made publicly available. So we will look into it. If you can email me separately, maybe we'll be able to share that one. So the problem right now is that, yes, it is tightly integrated with our internal Microsoft pipelines, but I think we can put that extra effort, just getting the relevant code out and putting it out in public domain. Right? So that's that.
There's another question on the Q&A. Okay, so Yoshan Leitner is asking if you thought about measuring energy needs before and after the distillation, right? So does it have an impact in terms of energy consumption doing the small or using the smaller models?
Overall energy consumption we did not really check. So that's one thing that we should basically probably care as well. See, I mean, for our shipping purpose, the idea was performance on CPU. So how much time does it take to come up with the final answer on CPUs? But yeah, power dissipation, energy consumption, honestly, we did not check. So that is something, yeah, I agree, could be important to check as well. Again, those things matter more for mobile phones, I believe, where the power envelope is very small. However, for machines, typically power is not that big a problem. The major problem is really coming up with the performance. So quick responses, essentially. That's the idea.
Yeah, I just have another quick one. So again, so you have this need for concatenating the query, the question, and the answer. And is the limit associated with this BERT-based approach of 512 tokens?
Good point. Absolutely. So we did that analysis as well. Fortunately, our things are pretty small in size. So for example, a query is not very large and question and answers are not very large, actually. So only in a few cases, I have not put up the numbers here, but probably only like 5% cases we did observe that it overflew. It basically had an overflow, but otherwise, no. Otherwise, that was not a problem. Yeah.
Okay.
Right. So in fact, we have been also more recently trying to really look at shorter ranges. So as of now, we use 512, but we are also looking at like 128 and smaller sized ones, so as to because we really do not need the large range for most of those questions, for most of those triples, essentially.
So there are still a couple of questions more on the chat, but
correct.
I think we can maybe now, we're already a bit late, so maybe we could move on to the second talk. And in the end, okay, we still have plenty of time to, discuss the different presentations within the session, okay? So I'll take note of these questions that are here.
Right.
And
Absolutely.
afterwards, we'll come back to them, okay?
Yeah. Thank you.
Well, thank you again. So I guess we can move on to the second talk of the session now. So this second talk is coming from Doctrine, a French company focused on providing access to legal information, okay? And Pauline specifically will talk about the challenges, let's say, associated with building retrieval services on this specific search domain, okay? So Pauline, when you want, I think you can share the screen.
Yeah, do you see my screen?
Yeah, so we're not seeing the presentation full screen, but we can see. Yeah.
Like this, it's okay?
Okay, now it's fine.
Perfect. So, hi everyone. I'm Pauline, a data scientist working at Doctrine, a French startup based in Paris. And today I will present you a Doctrine case study, and I will show you how we help French people searching the law in France. So, sorry, I will start with a brief introduction about the company and our search engine. And then I will introduce you how we built the knowledge graph and the legal graph that we use in order to improve our search engine. So Doctrine is basically the Google for law. So this is a French startup created in 2016. We are today around 100 people. And well, the main challenge that we have to face in France is the very, very huge volume of data in the legal field. There's around 4 million court decisions per year, also a lot of legislation and a lot of legal commentaries. And well, basically before Doctrine, the only search engine that people had was exactly the picture that you can see on my screen. So this is very complicated to find the legal data. We also have to deal with a lot of heterogeneous data. We have to deal with PDFs, HTMLs, XMLs, etc., etc. And it's mostly unstructured data because it's natural language processing. It's natural language, so we do a lot of natural language processing at Doctrine. And there's also the challenge of the domain specificity, because the legal domain is very specific, the language is very specific, the way of writing is also very specific. And so, of course, the way people search for the law is very specific. So this is basically how our search works. So there's different modules in it. So the first one is document understanding. So we try to understand better a document, how it is structured, what does it talk about, etc., etc. We also have a module about the query understanding. We try to understand what is the user intent. And these two parts feed the matching parts that we are currently doing with Elasticsearch. And then on top of the matching, we do some ranking. So we first use the ranking of Elasticsearch with the Elasticsearch score, and we add a re-ranking model on top of that. And today we are using LambdaMart from an Elasticsearch plugin. So if we want to improve our search, we can work on, well, 3 different aspects: the ranking part, the query understanding part, and the document understanding part. So, and actually, if we work on our document understanding part, it will help us improve not only the matching part, but also the ranking part, because we can add some features into the ranking. So we focus a lot on the document understanding part, and especially on our knowledge graph. So I will introduce you how we build this knowledge graph. So as I said, we manipulate a lot of different kind of data, court decisions, legislation, legal commentaries, but also companies, entities, lawyers, law firms, etc. And all these entities are related to each other. For example, a decision can quote a legislation, a legal commentary can quote a decision, a lawyer is involved in a decision, etc., etc. So here we have to, we deal with a real graph, and understanding this graph will help us understand each entity, each part of this graph. So this is a very huge challenge. So in order to build this knowledge graph, there's mostly two different processes. The first one is the detection part, and the second one is the entity linking part. So for the detection part, the goal is to detect the entities referring to other entities inside the documents. And the entity linking part, it is only be able to retrieve the unique identifier of the detected entity inside our database. So if I develop a little bit the detection part. So first, well, I didn't say that, but another main challenge that we have in the legal field is that we have a very few label data. So we have unstructured documents and a few labels. Sometimes we have, but it's very rare, So we have to label our own data. And so for that, we use different methods. We have automatic methods using regular expressions, for example, and we also spend some time labeling manually some documents. So we work with our legal team, and we use a quite famous tool now called Prodigy, which is an annotation tool provided by Spacey. And we fine-tuned it a little bit for our own use case, but we spend some time on the labeling part. And so then the goal is to detect, so not only the entities, but also the contextual information that will help us identify the entity. So for example, a lawyer in France is assigned to a geographical zone. A lawyer works in Paris or in Lyon, for example. And this is a very interesting information in order to be able to identify this lawyer. So we detect not only the name of the lawyer, but also its geographical zone, its internal ID, etc., etc. Because there can be a lot of homonyms, for example. And so for this part, in order to detect the different entities and the different tokens, we use a named entity recognition algorithm. Today we use the one from LAMP from 2016, which works quite well. So this is basically a by LSTM and conditional random field on top of it. We also use our own word embeddings because, as I said, the legal vocabulary is very specific. So we fine-tuned our language model in order to have word embeddings very specific to the legal domain. And then on top of that, we have the by LSTM layer, and then a conditional random field in order to take into account the local correlation between tokens. Okay, so now that we have detected entities and information related to this entity, we want to retrieve the unique identifier in our database. So this is actually exactly a search. We have a query on the left with the entities and other information. We have a list of documents on the right. So actually, this is exactly that, like a search problem. So for this one, we use also Elasticsearch and learning to rank algorithm with some feature engineering on top of that. This is actually exactly like improving the search of a navigational query. So this is interesting because I said that in order to improve our search, we build a knowledge graph, but in order to build the knowledge graph, we use the search. So it's interesting, and we will see later that on this part, it's very focused on the navigational queries, and then the knowledge graph will help for more informational queries. Okay, so now that we have our knowledge graph, so we have entities linked to each other, we will see how we use it in order to improve the search. So if we look back at our search framework, we can see that the document understanding feed the matching part. So we will see how the matching part can be improved with this document understanding and legal graph stuff. So if we take a legislation entity, for example, a legislation article, so now this legislation article is linked to a lot of court decisions and a lot of legal commentaries. Okay, cool. So what we can do first is building some custom features. For example, the number of comments linked to a legislation article. Why? Because the number of comments is a pretty good indicator of the relevance of a legislation article, because the more a legislation article is commented, the more it is important and relevant. We do that. We do a lot of custom features like that. And we can also enrich the vocabulary. So I didn't say that, but so the language is very specific in the legal domain, but each legal entity has its own language too. It means that the vocabulary used in court decisions can be quite different as the vocabulary used in legislation that can be a little bit different from legal commentaries. For example, in legal commentaries, it's more common words. So if I take, for example, an American example. I didn't take a French one, neither a Portuguese one, sorry. So, for example, let's take an example of a legislation on the rights. So, act to provide for reconciliation, etc. This is the formal name of a legislation, and this is how the legislation will be referred into court decisions or legislation. But in legal commentaries or in news, it's often mentioned as trans tax cuts, which is quite different. And there's no way we can guess that. So if we manage to link legal commentaries with court decisions, we will detect automatically that actually the vocabulary linked to this legislation is often trans tax cuts. And then we can enrich the vocabulary of the decisions and of the legislation, so that when the user will search for trans tax cuts, he will get the correct legislation or the correct court decisions. We also enrich our vocabulary with a lot of synonyms. So, well, first we have a list of hard-coded synonyms. This is quite simple. And we also use embeddings. So as I said, we trained our own embeddings, fine-tuned on the legal domain. So we are able to detect automatically synonyms in the legal field. What was interesting is that we managed not only to get synonyms of common words, but also of companies. For example, I took here two French companies on bank and insurance, and they are involved in quite the same cases. So their embeddings were very close, and this is actually very interesting for the search part, that if a user is looking for AXA, he may also see some stuff about BNP Paribas, which can be very interesting sometimes. Okay, so as you can see, we focused a lot on the vocabulary of the entities and their linked entities. But what we want to do more and more is to be able to have a document deep embeddings and dense embeddings using classic language models, for example, like BERT. So we started to do that. We are able today to build document embeddings, and we are using them for text classification, for example, but today we don't use them for the search part. We also want to do more and more graph embeddings, and it's very interesting because during this week, I heard a lot of talks about graph embeddings and how it's very powerful in order to predict new links, for example, and this is actually exactly what we are doing at Doctrine. So this is definitely a next opportunity for us. Another interesting thing is that since the AI applied to the legal domain is quite new, there's no very clean and exhaustive ontology on it, compared to, for example, the medical domain, where the ontologies are very exhaustive, and there's quite a lot. So definitely we have to work also on our own ontology on the legal field. And another opportunity is to try to understand better the latent document structure. Why? Because legal documents, for example, court decisions, can be very, very long. So this is first a challenge for the document and the embeddings part, because BERT is very good for short text, but for very, very long text, it's quite different. And actually in a court decisions, not all paragraphs are important. Some of them are more important than others. For example, the arguments of the judges are more important than the facts, the description of the facts, for example. So other projects focus on this kind of stuff. So there's a very huge new opportunities to discover, and we are currently working on it, and it's very interesting challenges. Well, thank you for your attention. If you have any question, I would be pleased to answer it.
Okay, so thank you, Pauline. Again, you won't be hearing the other people in the call clapping. You'll just hear me.
It's cool.
And yeah, so we have already some questions here in the Q&A and in the chat, right? Very interesting questions, actually. Okay, so I'll be starting with actually the first one here, which concerns with adaptation specifically to French law and to the French language, right? So one of the first questions here, Andrew McFarlane was asking this, relates to how you would adapt the knowledge graph part of the system to another domain. Let's say, for instance, the UK or the US legal system. Okay, so what would be the challenges associated with adapting the knowledge graph to domains other than the French law?
Yeah, this is very, very interesting. And well, actually, Doctrine has the ambition to go abroad and not only in France. So this is a question that we have actually. And so first, there's two different types of law. There's the civil law and common law in the UK or in the US. So we try to understand a little bit better how these two systems are different, but actually, so this is different because the common law is more focused on court decisions, whereas the civil law is more focused on the legislation. But what is interesting is that it's actually quite the same. Court decisions are quoting legislation, legal commentaries are quoting legislation, decisions, etc. So the goal is to build algorithm that will be able to generalize on other languages. So typically, named entity recognition, as soon as we have a labeled data set, we will be able to apply it to other languages without any difficulty, I think. But yeah, that's a good question.
So still in connection with that issue of adapting to other domains, okay? So for instance, Jochen Leitner was asking if, well, so the system as it is, it has NLP components, let's say, focused on the French language, right? So are there challenges there? Are there particular NLP components for which you feel that the performance isn't quite there yet, and ideally you would like to have better NLP tools in order to help in this type of work?
Yeah, it's interesting. Indeed, the NLP tools are mostly developed in English first. Well, in French, for example, so we tried the Roberta French model called Camembert, which worked actually pretty well. But on some stuff, for example, part of speech, this is working very, very bad. So we tried different stuff with Pacey or the Stanford parser, and this is not working very well. I think this is not working very well on French language, and especially on the legal language, where it's very specific and the sentences are not structured the same exactly, so it's not working well. And sometimes we can fine-tune the algorithm, but sometimes we cannot. And for example, if you want to fine-tune part of speech algorithm, it would be quite impossible because it's very complicated to label data and this kind of stuff. So yeah, well, it depends. For part of speech, it's very bad. For word embeddings, it's pretty good for now. I mean, we managed to do some interesting stuff.
Yeah, so here in the chat box, Debashi was actually asking, well, so he was making a comment actually related with this idea of, well, having documents that are long and usually complex with technical, with the technical vocabulary and the technical jargon being used. Okay, so he was specifically asking if that also impacts how you match queries provided by the users against documents, right? So you were mentioning that word embeddings, for instance, help in that. So is this taken into account as well? Things like synonyms or semantic similarity between words when attempting to match queries and documents?
Yeah, the fact that documents are long, you mean?
the long and the technical, well, terminology that is used within these documents, right? So the two factors associated with the complexity in these documents.
Yeah. 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 So for the embeddings part, so this is definitely a challenge, and that's why we are working on the latent structure of decisions. So for now, what we try to do is to embed first each paragraph of the decision. So not considering the whole decision, but each paragraph, and then add kind of attention layer in order to focus on the important paragraph, not the whole text, but only some specific parts of the text, so that, yeah, the algorithm can forget all the other text that is not relevant at all. So that's what we try to do, and we already did that, and more on classification tasks, stuff like that. On the search, for now, we don't really exploit this. And so we use Elasticsearch on the BM25 metric. Is supposed to be quite adapted to long documents, but yeah, that's it.
Okay, so on the Q&A, there are still a couple of questions there. So for instance, one is coming from Joshen Leidner. So he's also asking if for future work, you consider tasks such as argumentation mining from these documents as interesting. Okay, so these systems that are able to mine from documents specific spans of text that correspond to claims or that correspond to premises and relations between how premises support claims. So legal documents tend to be very argumentative and follow this structure, right? So do you think techniques from this field of argumentation mining could also be used to enrich the representations that are built from these documents? Do you have plans regarding that?
If I understood well the question, the idea is to be able to use what is done on legal reasoning and stuff like that in order to understand.
And also argumentation mining from text, trying to build graph representations similarly to what you're doing, but in which the structure that is being captured is more related to how arguments are presented within these documents. You see, what are the parts of information that support the conclusions that are being taken? Yeah.
That's a very good question. Actually, we don't do that at all today. But yeah, for example, well, at least in French court decisions, you often have the arguments of the lawyers and then the arguments of the judges. And the judges sometimes agree with lawyers' arguments, and sometimes they disagree. So the goal would be to indeed to be able to distinguish the different arguments, and then to be able to understand if the argument of the lawyer has been validated by the judge or not. This is definitely something we want to do, but I think it's very difficult. So we didn't focus on it today, but yeah, it's definitely one of the main challenges. And I think that I think, but this is more an intuition, in France, it would be maybe easier than for the UK or for the US, because it really relies on the legislation. So an argument is often backed up by a specific legislation, a specific article. And so we could use these links between legislation in order to detect the different arguments. Whereas in the US or in the UK, I think it's not that simple, because it's more about the precedent cases. So I think it's difficult to map an argument to something very concrete. So yeah.
Yeah, so there's some previous work on argumentation mining, right? But you're right. So this is still quite a challenging task. Okay, to consider.
Yeah, I was at the conference called ECIR about the AI applied to the legal domain last year, and this is a very there's a lot of research about this stuff. So it's definitely not I mean, it's not completed yet.
There's still in the Q&A one question, particularly interesting one. Okay, so Gineke was actually asking how you deal with the evaluation of the search system, right? So you have a search engine, you, I imagine, want to be performing tests in order to assess if it's indeed accurately, well, solving users' information needs and providing relevant results. For that, do you rely on, let's say, more laboratory experiments, or do you instead use A/B testing? Okay, so what's the type of methodologies that you use in order to evaluate the system?
Very good question. So today we have, actually two different way of evaluating it. The first one, in order to help data scientists iterate on the algorithm, is benchmarks that we have built with the legal team. So we took different queries of our users, we split them into navigational queries and informational queries, and then the legal team helped us label some data. This is not that simple because there's not one ground truth. I mean, two different lawyers will wait for two different outputs. Sorry. We wait for two different outputs depending on what kind of field they are working on. So there's no really a ground truth, but it can help us iterate a little bit. And then when we are quite confident about our algorithm, we put it into production with some A/B tests, and then the user is clearly the one who will decide if the algorithm is better or not. And we look at the CT or the click-through rate and stuff like that.
Okay, so thank you. So I guess this kind of concludes, okay, this first session. So we had planned for a third speaker. Unfortunately, he could not be with us today. As we still have some time, I would probably invite Manish to, well, turn on the microphone and maybe come back here to the call. Actually, there are some similarities, let's say, between the two presentations that were given in this session, right?
Yep.
And for instance, for your particular system, during the talk, you, let's say, mentioned that you are currently using Elasticsearch with a learning to rank model based on LambdaMart, right? So for you specifically, do you think it would be interesting to move towards ranking approaches also based on neural networks and representation learning, right? So ranking approach is based on a French version of a model like BERT, or do you think there would be too many challenges, for instance, in deploying something like that, right?
So the question is can it be interesting to use more deep learning re-ranking methods?
Exactly.
Yeah.
Exactly. Yeah.
Well,
is that something in your current plans?
Yeah. Well, sure. So I think today the deep learning methods are working quite the same as LambdaMart. So today it's not, I mean, it's not much better, and I think it's more difficult to develop into production. So on the short term, I think we will focus on the document understanding part with deep learning more than on the re-ranking part, because I think we have more to gain and to win on the document understanding part. But definitely, for sure, we will use more smarter methods for the re-ranking parts when it will be more easier to use. For the document understanding part, it's very easy because, for example, I think you know it, but the company called Hugging Face has done some open code on their GitHub, and the code is quite clean and we can use it very easily. So it was very easy for us to train our own language model. I think this is not the case for the ranking part, where it's more complex. So yeah, this is definitely something we have in mind, but not on the short term.
So within your Lambda Mart model, are you considering by now specific features, well, that are specific to this domain, to the legal domain? So within the features provided as input to this Lambda Mart model, are there particular aspects there that are specific to this domain?
Yeah, that's what I called custom features on my presentation, but I didn't develop a lot indeed. So yeah, this is very specific. And actually what is interesting is that it's very specific to French, to the French system. I'm not sure. I don't know very well the US system or the UK system, so I don't know. But so there's the number of commentaries. We use also so I'm not the one who worked on this, so I don't want to say something that is not correct.
Yes. Yeah. Go ahead, Pauline. Sorry.
Sorry.
No, I was basically just saying, Bruno, to add to the question that you were asking. I mean, at Microsoft, right? Of course, for search also, we have always been using, BM25 and those kinds of matches. But more recently, we have also shipped a BERT kind of model there for ranking, and we have seen like significant gains there. Of course, it is at the cost of compute and so on,
yes,
but
yes.
we do see significant improvement. So, I mean, I think, Pauline, I completely take it that yes, it does involve significant infrastructure things. But at some point, if you find it worth, I would push for it. I mean, you do try transform models plus knowledge distillation kind of a combo, and see if it helps. That said, I don't know French, so I'm sure your extra features might be doing some good magic as well. But maybe you can combine them with transformer-based features and then see what happens.
So prior to last year, I think one could make the claim, okay, that these classical learning to rank approaches were still outperforming representation learning methods. But yeah, from 2019 on, people have been reporting some gains, right?
Yeah.
So in your specific system for fact retrieval, have you tried using a feature-based approach based on something like Lambda Mart as well? Have you compared that?
So
yeah,
absolutely. So in fact, our candidates are obtained using BM25. So
yeah, but more than BM25, have you tried combining BM25 with other, let's say,
linguistic features and so on,
signals within a model like that?
Yeah. So we did. In fact, we did build a Lambda Mart kind of a model with various kinds of linguistic features. I mean, all kinds of things like potential. So we also did try to learn sort of translations, like, hey, if this is in the question, then what is it? You can expect an answer. In fact, there's a whole bunch of literature which does that. So there are previously proposed methods for question answer, for FAQ retrieval itself, which use feature-based methods. And we do see that this is better. This is much better compared to hand-engineered features. So that is there. Yeah, I mean, and the same goes for the overall ranking story as well. I mean, overall ranking also, but then in overall ranking, at least we have not replaced the system. I mean, I think it is it's actually a combination of hundreds and thousands of signals plus transformer-based signals. Yeah.
Okay, so well, thank you again, thank you both.
Thank you so much. It was a great session. Just to tell you, we have a follow-up PAKDD paper.
Session, two very interesting presentations.
Absolutely.
Yeah, so I'm not sure. So if the people attending the session, if you have additional comments, additional questions, please do try to leave them here on the chat window or on the Q&A. We'll either try to, tell this here or maybe promote you to be able to speak in the session. Yeah, so if there are no more comments, I guess we can close this session now. Okay, so we'll be having a coffee break now. And the second session of the Industry Day is planned to start at 11:20. Okay, so I would just ask the speakers in the session to try to be present a bit before so that we can check that everything is okay. I noticed that some of them were previously in the call already and were attending the first session. So yeah, congratulations again. So hope you enjoyed the session, and we'll be back here reconvening at 11:20. Okay, so now it's, I guess, time to enjoy the virtual coffee break, or well, the coffee that
is
you have at home. Okay, so bye bye. Thank you, and see you at 11:20.
Thank you.
very
Bye bye.
much.
Bye bye.